Thank you. So let me move to the introduction of our work. Every year, medications get more complex and personalized, and it's possible to boost the efficiency of biospectral compounds by employing nanocarriers. These structures have special qualities such as biodegradability, biocompatibility, and rather simplified synthesis. And moreover, they should be adaptable for every gas. So when the molecule meets all the parameters, it can considerably increase the impact of the treatment by targeted delivery, allowing for a reduction in the drug concentration needed for sustained effect over a long time period, and do it without exceeding the toxicity threshold. Because it enhances medicine molecule solubility, it also opens the door to the numerous prospective compounds that were previously unavailable due to their low solubility. So the nanocarriers can have a variety of architectures, such as linear, star shape, or hyperbranched, and so on and so forth. But some contaminants may develop as a result of the simplified synthesis, and their structure is similar to that of the target product. So this results in overlapping of the signals in the standard proton spectrum, and after we use this spectra, it results in calculating errors. And the only way to estimate the component proportion in the signals in the proton spectra is to do a diffusion experiment dosing. So this technique yields a variety of proton NMR spectrum with varying magnetic field gradients. And the processing consists of determining the dependency of intensity of signal to the gradient of magnetic field, and after that, approximating this dependency using the weighted sum of exponents. And the general law can be seen on the slide. So each exponent has a cell diffusion coefficient that corresponds to the mobility of the particle and hence with its mass. And NMR software has several conventional pockets to process DOSY data. However, it doesn't work well with the components of similar structure, and as a result, manual data processing is required, and we're confronted with the poorly conditioned task. So we can approximate data by summing several exponents, but as the number of exponents grows, we can reach the point when several variants are good enough to describe our data with non-zero noise. And furthermore, due to the time constraints, we can obtain only 128 points for each experiment. And even in this case, the experiment lasts more than 2 hours. So it's critical to identify technique constraints in our case and provide answer to the following questions. How many exponents are we able to resolve? Or what is the smallest ratio of diffusion coefficients that we can resolve? What is the smallest piece of the component that we can resolve? And can we interpolate our data using some calibration? To get these answers for these questions, we need to do a series of experiments with few components. But we cannot be sure that the components we use for nanocarriers, such as blocks of copolymers and homopolymers, are pure enough. And we want to investigate this. So we decided to employ a variety lengths of polyethylene glucose, just packs, to create mixtures with a known composition. And as we may compare the results of approximation with initial conditions of mixing and determine whether this approach is good enough for our systems. So to begin, we provide those experiments for pure pack solutions to ensure there are no impurity and to create a calculation curve. We discovered that 4 of 5 samples of packs are pure enough for our study, but the pack with the highest mass contains more than one component, and so we decided to omit it from further mixing and composition. So the masses of packs are known, but we decided to provide a standard proton spectrum to calculate the mass with the characteristics from the spectrum, as we will do in study with Dolgoprodniy and homopolymers. We made a calibration curve. As this polymer cannot be described accurately by the model of small spheres, we can only use some empirical law to connect cell diffusion coefficient with smaller mass. Survey of the literature showed that power dependence is suitable for polymers, and after we make a calibration curve, we counted the potential for this law. So going to the next step, we made a composition of two components, two packs with smaller mass 8,000 and 1,000 daltons. And here on the slide you can see the results of approximation by 2 and 3 exponents. The weight portion is out of interest, and with the yellow dots you can see the initial conditions of mixing, and with the blue dots you can see the results of the 2 and 3 exponential approximation. Both of these approximations are quite close to the initial data, and furthermore, despite the changes in the content and the viscosity of the systems, the cell diffusion coefficient is also quite stable. When the components differ 8 and more times, we can conclude that even in these systems, we can use cell diffusion coefficient for calibration and understanding which mass we operate with. The next step was reducing the differences between components, and we investigating the different compositions of polyethylene glucose with mass 1,000 and 4,000 daltons. And also you can see here different compositions, different proportions of components, and with yellow dots is initial proportions, and blue dots are approximations by 2 and 3 exponents. The error is higher than in the case of the previous mixtures, but still we can define the proportion with accuracy of 10%, and still diffusion coefficients are quite stable. So in all previous cases, approximation by 2 or 3 exponents were better than non-exponential fit, and this confirms that our method is quite sensitive to differ systems with contaminants from pure systems. But it doesn't answer the question which approximation is better, because in case of 3 exponential fit, that seems to be more accurate. We used 5 parameters, and sometimes programs that make the fit, they can define these parameters not in the right way because of the non-zero noise. So we decided to make an additional experiment with a mixture of 3 components and the high number of points. In this case, is 1,024 points for this experiment, and you can see the black line is experimental data, and red, blue, and green lines is for exponential fit. And also, it can be seen that mono-exponential fit has greater residual role from the experimental data, and 2 and 3 exponential fit are quite similar and shows nearly no difference between them. but both didn't show the presence of the third component in the system. So in this case, we can conclude that three exponential fit is it's not better than two exponential fit. So to summarize, we discovered that approximation of DOSY data by the sum of several exponents allows us to differentiate systems with contaminants from pure systems. And also, we noticed that DOSY works stably with cell diffusion coefficients that differ by 4 or more times when we talk about two-component systems. And it's sensitive to component proportions of 10% or above in the same systems. Also, we showed that cell diffusion coefficients are rather stable in mixtures, so it's possible to use calibration curve for further studies. In our plans is to work with different models of approximation and use statistics for more accurate error estimation. And after we get the optimal parameters for approximation and for experiment conditions, we will use this method for block copolymers and homopolymers because these systems have some inclusions which are hard to remove, but still they should be counted when we calculate characteristics of block copolymers for each guest we want to include in this system. So now I'm ready to answer the question. Thank you for your attention.
Thanks very much, Valeriya. Questions, please.
May I ask a question? The thing that you do is actually a very old problem, and it was considered in literature for last 40 years, I think. The general conclusion was that the mixture of two polymers will not give the same diffusion decay as just the sum of two individual components. And another question, can you please show the 7th slide? You talk about some fitting by 2 and 3 exponents, but when you show results for 3 exponent, you just have the last coefficient equal to 0. So is this meaningful at all? And I think you should present the data in the logarithmic scale where the actual dependence is more clearly seen.
Mm-hmm. Thank you for the question.
And it's absolutely not clear what that means on the x-axis. So you should on the slide show it too. This is probably squared thing. So in logarithmic coordinates, there should be a straight line for one exponent.
Yes, thank you for your questions. Well, I will start with the first question about this problem. Yes, I know that this problem is quite old, and researchers tried to solve it, and some pockets in software is the answer for the biggest part of this problem. But in our case, we want to study those experiments for the systems with very close structures. So it begins with our study of block copolymers and homopolymers when we observed in the proton spectra that there are some disagreements between the number of active centers and number of change that were added to the hyperbranched polymer, but the results of the studies of chromatography showed that it was a quite pure system. So we decided to provide those experiments and show that there are some contaminants. but we wanted to count the weight portion, and we found out that there is no investigation of the systems like Dolgoprudniy homopolymer that will guarantee that the weight portion we observed is close to the real situation. So we decided to provide some experiments with polyethylene glucose. So we found that it's a new problem in the complex of all problems. In this slide, we just put the data of the approximation. Of course, when the approximation by 3 exponents shows one parameter is 0 or close to 0, it may be not mindless, but how to say, it's the result of approximation, and I think I should show it to make the sense that in our case maybe there is no difference for 128 points between 2 exponential feet and 3 exponential feet.
So it's not a problem of experiment or the data and the number of points, it's just a problem of your exponential approximation. And you also should take into account that the points which are less in intensity, they give less contribution to the feed. So actually the later part of the diffusion decay do not contribute at all to your fitting. So it's a wrong way, I think.
I can't agree that it doesn't impact on the whole approximation. We will investigate this question. But and about the graph, yes, I thought that it would be not maybe over-parameterized if we put the whole number of parameters, its square gradient with some time parameters. So it's the same as you put in your presentation. I watched it and I thought about it. And maybe it's better to show this data in logarithmic scale, but I thought that the raw data may be also interesting. We now try to also communicate with data scientists, and they proposed one of the variants for this approximation, which uses logarithmic scale and linear approximation for the parts of this data in logarithmic scale to understand which components, how many components, and the weight of these components we have. So, but now it's not ready, and I want to put this information in the further presentations.
Thank you.
If I may, I'm just going to add one short comment on the subject of fitting. So let's say, you know, you're fitting with a single exponential, and that's obviously not enough, and then 2 exponential fit, and that appears to be right, kind of an optimum, and then 3 exponential is overfitting, and 4 exponential is a gross overfitting, and so forth. There is a statistical criterion that maybe you heard about. It's called Akaike information criterion that allows to discriminate between those situations. So it's sort of mathematically rigorous based on residuals, degrees of freedom, and so forth. So that's something that maybe also is going to come up in your analysis. And with this, let me thank you once again. Thanks very much, Valeriya.